today, so that you can get help from Ishmael, and if necessary, myself later on in the day, so that you're ready to go tomorrow when there will be no one you can actually dial into Zoom to get help from. Yeah, it's just Xcode that you actually need installed. We'll sort of cover why that's the only thing you need, and but it takes a long time to download. So definitely get on with that as soon as the lectures are over today. So we've got there's a fair amount we need to actually cover today to get us up and running with iOS. So I pushed out the Android quiz until Tuesday next week, so that we can make sure we've covered everything and do it comparatively slowly. We'll get during the two sessions this morning, we'll get you all to actually confirm that you can install and get very simple iOS applications up and running, so that you are ready to make a good start on assignment 4 as soon as you've got assignment 3 out of the way. Okay, so for the first section before the break, we'll just have a look at where iOS came from. Its story is somewhat different to how Android came into being. And then we'll actually look at we'll dive straight in as to how we develop applications for iOS. We'll look at the language we're going to be using, which is Swift. So we're using Kotlin for Android. We use Swift for iOS development. Xcode is the development environment. It's the equivalent to Android Studio. And then we'll actually have a look. We'll have a look at two examples, actually, just a very simple Hello World one, which will get everybody to install and make sure we can get that running. And then we'll have a look at an infix calculator, same as we did for Kotlin. The difference being is that there's no non-UI step in iOS development. We'll dive straight in and have very simple user interfaces. We'll be looking at more complex user interfaces on Tuesday because you'll need that for your assignment 5. But right now it's very, very simple. So the code, the logic of what we're doing is the same as we did in for Android. It's just that we're using Xcode to develop iOS and Swift as the language. Okay, so for those of you who've got a Mac but you haven't installed Xcode, start installing it now because it takes a long time to actually download. Whilst we're actually talking about the introduction to it. Okay, so history of iOS. It traces its lineage back to the late 60s, where AT&T, Bell Labs, developed the Unix operating system and started using it commercially as opposed to for internal research and development purposes, late 69, early 70. Only ran on a DEC PDP 1120. It was this is version 1. And then very quickly, there were a number of releases that became available. So Unix version 1 was written in machine code assembly. The 1972 we had Unix version 4, which was completely rewritten in C, and it became very popular, and universities started asking for copies of it, including many in the University of California system. And so very soon thereafter, Unix version 5 came out and was licensed for, I believe, $1 to educational institutions. And very soon thereafter, commercial organizations, airlines, banks, and so on, government institutions said, hey, this new operating system looks pretty cool. We would like to get our hands on that. So AT&T started making it available to commercial organizations. And it was quite expensive. So it's approximately the equivalent of around $120,000 today. And very soon thereafter, um, uh, University of California, Berkeley released their own version of Unix called the Berkeley Software Distribution. Um, it was a completely modified version, so there's a lot of AT&T code in there, but they introduced new concepts into the operating system and a lot of new command line tools that hadn't been in the Bell Labs version. And people, particularly in universities, liked that version. So the Computer Systems Research Group was responsible for that at Berkeley. Um, and then that was very popular. They were distributing that on tapes to universities all around the world. Um, this is pre-commercial use of the internet. And then AT&T and the LH released Unix System 3. But now its prices dropped significantly. So you could actually license System 3 from AT&T and actually resell it. So, for example, if you were you had a little software company that wrote software, say, for gas stations. And obviously the gas station software was something that you developed, but you could actually install it onto an AT&T Unix system and resell that, and only have to add another $100 on top for the licensing fee to AT&T. So this is the point at which Unix starts taking over the world. If you're not aware, the operating system wars are over, and Unix won. The only holdout against Unix is Windows. And it was always going very, very well. But AT&T were a little bit surprised that they had this little operating system that was proving very successful. But they actually started, AT&T started manufacturing their own computers. There was a day when you could actually buy a small Unix machine that was badged AT&T, and they actually manufactured them themselves. But the problem for AT&T at the time was that they were the largest company in the United States. They had a monopoly on telephones. They were just known as the telephone company. And so the federal government took a close look at that and introduced an antitrust case against them and forced AT&T to split up their organization into the Bell system, so the baby bells, as we know them today. So Pacific Bell, that's where it came from. Previous to that, it was one company for the um, uh, uh, entirety of the United States. One of the things that they were forced to do was divest themselves of their computer division. So they had to sell their business that actually made computers. And they weren't forced to sell Bell Labs, but basically now have a problem because they have an operating system and nothing to run it on. So then, at the same time as the antitrust case, System 5, interesting, there was no System 4. It went straight. There was no System 1 or 2 either. There probably were internally, but they never got released to the outside world. So Unix System 5 was released, but because AT&T didn't have a computer business anymore, they released it to third parties like Hewlett Packard and the company I used to work for in the UK, ICL. So System 5 was the first version of AT&T style Unix that we would recognize today when we're actually using modern Linux systems. And this was around about the time that I was writing operating systems, and we used System 5 Release 3.2 as the basis of our operating system in the UK. And then everything was sort of good for a while. You basically had two versions of Unix at this point. You had Unix System 5 from AT&T, and you had BSD from Berkeley. But AT&T took a very close look at BSD and realized that large portions of it were copyrighted. They owned the source code, and BSD had just stolen it, and were using it without permission, and were actually reselling it to commercial organizations, which is illegal. It is copyright infringement. So AT&T made the copyright claim, and they won. And Berkeley were required by the courts to either stop selling BSD or create a version of it that has zero AT&T copyrighted code left in it, which is what they did. So it took them a long time to get rid of all the AT&T code because that was the good stuff in the kernel. And so BSD 4.4 was released, and then immediately everybody from CSRG was disbanded. That's a polite term. They were fired. But it was convenient because a little bit before that, Steve Jobs had been fired from Apple, the company that he founded with Steve Wozniak. And he'd gone on to form Next Computer, and Next Step OS was the operating system for these. If you've never seen a Next Computer, just Google image it. It's a perfect cube, black cube. It looks like a very futuristic thing even today. So Steve Jobs actually hired all the people from Berkeley who got fired, and Next Step was BSD 4.4, give or take a few polishy bits on the outside. So then, slightly thereafter, Apple realized their mistake. They bought Next Computer, lock, stock, and barrel. And part of and they wanted Jobs back. They didn't really want Next Computer, but that was part of the deal. They said, look, if you want me back, you have to buy my company. And from now on, every Apple computer will run a version of the Next Step operating system, which is BSD 4.4. And this is a big deal because the original Mac OS had been running for many years at this point, decades at this point. But it was his own thing. It had been entirely developed internally within Apple. It had no similarity with any other existing operating system. But they wanted Jobs back so desperately, they agreed to that, and the original Mac OS was abandoned. And from then on, all Apple devices, or computers at the time, they didn't realize they were going to have phones and watches, but all computers from then on were running BSD 4.4, which went through a number of different names, including OS 10. And it's now back to being called Mac OS, which is a bit confusing because it's nothing to do with the original one. So this sort of went on for some time, and about a decade later, obviously the world was changed significantly when the very first iPhone was released in 2007. So iOS, the iOS 1, was based on Mac OS 10, which was itself a BSD 4.4, which was itself AT&T Unix way back from the late 60s. And that's where we are now. So every Apple device, with the exception of some of the lowest spec Apple Watches, and that information might be out of date, but basically everything runs operating systems that can be traced back to the original work from AT&T. So we have the long-winded story, but the same as we have on Android. Android is Linux. And iOS is Unix, and so as well as all the server infrastructure, all the mobile phones in the world, give or take, run a version of Unix. Okay, so versions, obviously we're up to 18.5, I think now, in the decades since the original iOS came out. They've changed their logo slightly over the years. But one thing that's actually very different it's not about the operating system itself, but Apple's approach to its support is how long they will support old versions. So we saw we had a slide last week sometime when we were looking at the different Android versions, and we were going to select one when we were choosing to build our app and say we want to target a particular Android version so that it will be usable on the majority of devices in the market that we are targeting. So if we're targeting a market with very low spec potentially old devices, we can do that. So in 2025, we can target an operating system that came out in 2008. Not a problem. You cannot do that in the Apple world. So they deliberately end of life versions of iOS. So this slide's a tad out of date. I was trying to find a modern one, but I couldn't. But the effect is the same. So as time goes by, so on the original iPhone, they supported 1, 2, and 3 of iOS. And then when iOS 4 came out, they said, okay, we're no longer going to support the original iPhone. You have to go to an iPhone 3G and so on. And then, as you can see, it's sort of with some slight oddities here. It's usually 3 or 4 versions into the past that get supported. So, and that's a very deliberate policy. They don't want you to be using an old iPhone. They want you to be using a new iPhone. So in my drawer, I have any number of old iPhones that can't support modern versions of the operating system. So they force me every few years, kicking and screaming, to buy a new one. You can't say it's right or it's wrong, but it's certainly very different to the Android world. Okay, so as we mentioned briefly on that history slide, let's go back. Uh, is that the programming language that NeXTSTEP is written in is called Objective-C, which is give or take C++. It's an object-oriented extension to C, and that's the language that the operating systems are actually written in. And for a long time, I can't actually remember which version of iOS it changed in, but for a long time, when you wanted to write an iOS application, certainly the first ones I wrote, 15 or more years ago, you had to write in Objective-C. And as someone whose favorite language is C, that's not a problem. But C and C++ and related languages have some issues, um, uh, which needed to be addressed. So Apple came out with Swift. You can still write in Objective-C, by the way, in the same way as you can still write Java for Android applications. You can write in pure Objective-C, you can write pure Swift, or you can write a mixture of the two. It's which is good for backwards compatibility. You don't need to throw everything away when they introduce a new language. But Swift is a modern language, same as Kotlin is. It's general purpose. It's not it's not the case that you can only use it for developing iOS applications. It's compiled, so you can compile it to any, well, not any, but most native architectures. So you could write a little command line tool in Swift, compile it, and it would run quite happily on your Mac. It wouldn't run quite so happily on your Windows machine, but you could actually do it. So it's a general purpose compiled language. Multi-paradigm, as we saw when we're looking at Kotlin, we can program in an imperative style, but we can also program in an object-oriented style. It is type safe. When we get into looking at JavaScript for cross-platform development, it's not type safe. That's deliberately untype safe. And it has type inference. We've seen this before. So it can actually work out the types of things if you don't explicitly tell it. So all modern languages can do this. It's a modern language. So it's been around for about a decade. And it says replacement for Objective-C, it can quite happily live side by side. And it retains some of the nice features from Objective-C. Dynamic dispatch, we'll actually see that as we go through the material today. It's an unusual feature for a language, but it's in there because of the platforms that the language is aimed at, and it certainly helps us in developing mobile apps. But it's what it compiles down to is Objective-C. There is actually an intermediary step. It goes from Swift to Objective-C into binary code. We don't see that step, but what it means is that we can use Objective-C that we've had for donkey's years. We can write C, we can write C++ code, we can bring that in all very happily. We don't need to rewrite it into Swift. We can bring it in and we can actually just use it in one app, which is very nice. Certainly for more technical apps where you will have existing significant investment in libraries of code that was written in C or C++, you can quite happily bring those in, just use them in your Swift application, which is very handy. And it also addresses an issue that was addressed by Kotlin, which is the basically null pointer exceptions. So this is the bane of life of anybody writing in C or C++, is that you end up with a pointer that's not pointing to anything. It used to point to something typically, but now it no longer does. If you try and then access that memory location, all kinds of things blow up within your application. Swift addresses that problem. It also has a lot of what we call syntactic sugar. So shortcuts, abbreviation, terse syntax. So the pyramid of doom, I'm sure you've all seen this, is where you have a piece of code where you have nested conditionals, and before you know it, the code is all the way off to the right-hand side of your IDE, and it's a sort of a pyramid on its side. So you continually go down, 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 down through nested conditionals, and the code gets very hard to read at that point. So there's syntactic sugar in Swift to allow us to not do that, which is I'm very thankful for. It's a very useful feature. As you would expect in any modern language, we have an extensible type system. So we have built-in types, a small number of simple types, as we have in Kotlin, and we can extend the type system. We can create new types based on the existing built-in types, and we can create new types based on the new types that we created previously. Again, you would expect this in any modern programming language. And unlike C, for instance, it actually has native support for concurrency. In other words, multiple threads of execution. We've seen this in assignment 3, is that we need multiple threads in a mobile application, if for no other reason than to be able to do network access. So we need to have multiple threads and concurrency and the ability to execute code asynchronously. So it will execute in its own thread, wait for things to happen, and then we need to have the ability to notify the user interface thread so that new things can appear on the screen. Okay, so we'll have a quick run through Swift. Swift is easy to understand once you actually get into it. It's a very familiar language if you've used any modern programming environment, which you have, if only with Kotlin in the last sort of week and a half. Okay, so things to remember in Swift. So basically, variables are always initialized before use. Again, contrast this when we get into JavaScript, which is not the case. And so you can't define something and then give it a value later. Array indices are checked. So if you try and access beyond the end of an array, you get an out-of-bound error. But that's done at compile time so that you can't index something beyond its limit and end up with something that crashes at runtime. Integers are checked for overflow. So if we go beyond the capacity, that will be checked. There's something called an optional. So we said variables initialized before use. Excuse me. But in some cases we want to say a variable is initialized in such a way that we regard it as having no value. It does have a value, but we choose to regard it as not having one. And this is a nil. Nil is different to null. And this is a concept that comes from Objective-C. And in Swift, these are called optionals. So basically, we can say in our code that this variable may or may not have a value. And they're handled explicitly within the language. which is kind of nice. So memory management automatic. We don't have to do our own tidy up as we would do in C or C++. Um, and it's not, although the effect is the same as a garbage collector in Java, the implementation is very, very different. There's no delayed behind the scenes garbage collecting. When something goes out of scope, it is the memory it was using is collected automatically by the Swift runtime. We do have error handling, so we can recover, try catch and so on. We can recover from unexpected circumstances. Um, uh, Again, as you'd expect in a modern programming language, type inference. So the runtime will work things out. When we assign a value to it, we don't have to say what its type is. Swift will work out what its type is based on its initial value. And something that's a little bit strange is that you can have variable names don't have to be ASCII. So, foo, bar, Bob, and Betty as variable names. We can actually use Unicode, so extended character set variable names. So you can actually have this is a sort of an invariant in your code for the value of pi that actually has the symbol of pi. Personally, I don't use it. Some people do. Some organizations would say this is a good thing. Some would say this is terrible. Don't do that. But it doesn't really matter. So here, pi has an inferred type of double because of its initial value. It's up to you whether you actually use that. But the important thing is the type inference. Okay, so we have regular variables, but we actually want which are mutable variables that could be changed. But we always want constant variables, so something that is set and its value cannot be changed. Um, and we have the usual unary, binary, and ternary operators, as you would imagine from any language that's inspired by C, int, double, Boolean, and so on. There's a number of collection types. Array, again, one that we're using frequently. Sets and dictionaries. And tuples for simple data groupings, very, very easy. And we want to use constants with a let, so that's an invariant. As we on the pi example on the previous slide, we use let because it's invariant, so that's a constant. Whereas something that can be changed is a variable, var. They're both variables, but one of them has a constant value; it cannot be changed. Whereas optionals are slightly different and very handy. So basically, we can declare something as being optional, and it either has a value or it doesn't. So I can optionally say it has a value that equals whatever the value is, or there isn't a value, which is different to saying it has some special value that we trigger off and regard as being unset. So basically, to actually get a hold of it, is we need to unwrap the optional variable. And so we start with, so give an example. So we start with a variable called name of type string, but the question mark says that it's optional and its an initial value is nil. So at any point in our program, it may or may not have a value. So if we want to unwrap it, unwrapped is a new variable, and basically if that successfully unwraps, then we can actually get hold of a number of letters that were in the original name. Otherwise, name doesn't actually have a value. That's expanded. Typically, you'll use it in a compound statement, and you're basically saying, if it has a value, I'll use it, and if it doesn't, I won't. Similar to features that we saw in Kotlin. So as an example where we'd use that, so we're doing this in assignment 3 in Android, in Kotlin. If something comes back from the API and it doesn't actually have a value for one of the attributes of a data entity, we would declare that as being optional. because it may or may not actually have a value. Okay, so in terms of obviously we've got our simple types, int, double, boolean, and so on, string, and collection types, also useful things, but we actually want to be able to uh, define new types, new data types, but also new functional types within our Swift code. So we have two different ways of doing it in Swift. We can structures and classes. They're closely related, but they're not the same. So for structures and classes, structures are a simpler concept than a class. But for both of them, we can actually add properties. So name would be a property of a structure or a class. We can have methods, so functions that we can call on the structures or classes. And we can get hold of values. Subscript means we're indexing into the structure or the class to get hold of their value. Initializers are not quite the same as constructors in other language, but they set up their initial state. And we can extend them. So we can create a structure or a class and then say, I want to create another structure or class based on the one that we have. You can't extend a class to become a structure, and you can't extend a structure to become a class, but you can extend the structure into a more sophisticated structure, and you can extend the class into a more sophisticated class. So we extend them to increase their functionality or potentially override some existing functionality. And protocols are the equivalent of interfaces in Java, where you declare a protocol is a definition. It's not something you can create an instance of, but you can say this structure must conform to this protocol, which is like saying in Java, this class must implement this interface. It's the same idea. So that we can actually have lots of different structures that all conform to the same protocol. And as a consequence, we can declare functions that accept an argument that must conform to a given protocol, but we can pass in instances of lots of different structures and classes, so long as they all conform to that protocol. This is fairly standard object-oriented technology today. So we have for structures and classes, but for classes only, they inherit. So we can say they extend a class, and we can actually check their type at runtime, which you cannot do for a structure. You can check whether or not it conforms to a protocol, but you cannot say, is this variable or object you just gave me an instance of a structure? Whereas we can check whether or not an object is an instance of a class. And unlike structures, they have deinitializers. So structures and classes have initializers, but only classes have deinitializers. So if there's something that you need to clear up once an object goes out of scope, maybe close a network connection, close a file that we've got open locally, that would need to be a class. And reference counting. So we can actually find, so reference counting means every time someone makes a reference to a particular object, an instance of a class, the system keeps a count of that, so that when one reference to that object goes out of scope, it can say, actually, well, how many other references are open? And if it's more than zero, it won't actually destroy the object. And structures don't have that. Okay, so structures are simple. We would use a structure in most circumstances, but we'd use classes if necessary when we want something a little bit more sophisticated. So classes carry around more bag and baggage. For a simple task, we use a structure. For a more complex task, we'd use a class. So another feature that Swift has, which is very nice, it's a moderately unusual feature in languages even today. This is called extensions. So we can actually take an existing object without really knowing anything about its structure or class, and extend it, add additional properties whilst it's running. So this is quite unusual for a compiled language. It's very common in interpreted languages. So it's Swift is sort of mixing its metaphors a little bit here, but they're quite handy. So you could take for instance the built-in string class and give it an extension that is specific to the purpose that you want to use those strings for within your app. So providing instant methods and type methods. So type method goes on the structure of the class, and instance goes on a particular instance, a particular variable that is of that type. And then there are others. You can self-study on them, but it's not a it's either something that you like and can think of ways to use it, but it's not something that is you will necessarily need to use in any of your assignments. So if we take an example here, so we have, so double here is a built-in type, and we actually want to use a special version of double for measuring distance. So we can do that by extending double, and whatever the value is, if you want to know what that distance is in kilometers, it will work it out for you. So obviously, and then if we say these are the extensions, the actual number is being held in meters. So the value of the raw double is say 12. That's 12 meters. Excuse me. If we actually want to get it in centimeters, we can just ask for that. I should give an example there. So this is, we say an inch is 25.4 millimeters. Then we can actually find out what that is in meters. So but the 25.4 is the value of the double. The .mm comes from here. So we can now actually get hold of its value actually in meters. Yeah. So the raw value is in meters, but we created it using millimeters. So if you've got types that you understand well, and you don't want to continually keep converting units in this particular example, you don't have to. You can extend the built-in types. And then if you put it in as feet, 3 feet is 3.ft, so it's exactly 3 feet. And then we can ask it what that is in meters. And that's done through an extension. Obviously, you could do that with helper functions. You could call a function and say, give me this value in feet as opposed to in meters. But if you're doing a lot of heavy data manipulation of specific types, as we are here, it can be handy to actually use an extension instead. The extensions are actually, we won't notice it in our apps, but the extensions run far more quickly than calling a function. There's no need to collapse the stack, extend it and collapse it when you call and return from the function. Excuse me. So that was a type extension just in terms of its units, but we can also we'd have a method extension. So here we're extending the built-in integer class, and we actually have a function extension on it, where we pass in the number of repetitions, but rather than passing it into a function, we can just say 3.repetitions, and it will do whatever we pass in as the task. So it's basically going to print hello exclamation mark 3 times. Excuse me. But we could pass in anything we like as the task inside the curly braces here. We could be printing something to the screen on the phone. We could be making a network call. Whatever we want to do, we'll just do it 3 times. And that's an extension to the integer. So this is a very, very terse way of doing this. This is a collapsed for loop. Now, obviously, the for loop is here, but we just reuse it as many times as we like. So extensions are cool. If you don't need to use them, but if you can think of a circumstance where that would be handy to you, then by all means go ahead and do that. Learn a bit of the language as you're doing it. Okay, so obviously we have functions. All languages have functions with a Pascal calling convention. Again, as many an arbitrary number of arguments with a single return. So we've got an arrow syntax here. This is not the same as an arrow function in other languages, but it's basically saying this function called greet, which takes a string and a boolean as arguments, will return a string. And as we can see, it actually does. Obviously, you can, if you don't want to return value, we just miss that off. So unlike in C where we have to return void, we can just say this function doesn't return a value and the runtime won't actually look for it. We have to have name parameters, so they're not positional, they're named. And we either return a value or we don't. But if we return a value, it's a single value. But Swift has a little bit of syntactic sugar, as we named about, and basically saying at the runtime, yes, we can only return a value, but we can destructure that return and return multiple values, or apparently return multiple values. So here we've got a minimum and a max. We take an array and it will return the minimum and the max. So what it's really doing is returning a single object that has two attributes. One is min and one is max. But the syntax allows us to say, well, what does that object look like? And so here where we return the current min and the current max, it's actually creating an object that has two attributes and returning that single object. So if we actually call that, straightforward, the bounds is now an object because there's type inference, remember? The bounds is now an object that actually has those two values on it, the minimum and the maximum. Okay, so in terms of Swift usage, that's pretty much as much as we'll do in the class. It's sort of we'll learn by doing, going through the assignments. But obviously, one of the important things that we've been looking at in all our assignments so far is testing. Swift, the Xcode infrastructure and the Xcode environment has a system called XCTest, which we'll be using. It's not actually the only testing framework you can use in Xcode, but it's the one that we'll be using. And there are, in the same way as we had two different kinds of tests in the Android world, we have two different kinds of tests in the iOS world, the Xcode world. So we have tests for logic components that have nothing to do with the user interface. And we have tests for individual UI components or entire applications. And we'll see this as we get into the an example in a moment. The principles are we have test cases, which is a test suite of tests, and we have test methods. These are the methods that actually, these are the individual tests within the test case or the test suite. Excuse me. So here here's an example. We have a table validation test, which is a class. So it's not a structure, it's a class. And it extends XC test case. So it's being set up, it is a test suite. And then we actually have a function within it where we're testing something specific. This example was just taken from Apple's documentation, by the way, and it actually has a fundamental flaw in it. Anybody like to spot what's the flaw? Not in the syntax, just in what it is that they're doing in this test. More than one assertion. So this should actually be two tests, both of which create a table. One of them which asserts the row count is not zero. Oh, sorry, the row count is zero. This text here is the error if this assertion is not true. And then I have a second one that checks that the column count is not zero. Because just to remind ourselves, the reason we don't do two assertions in one test is if this assertion fails, this one is never evaluated. So we might have got the row count wrong, but our column count was correct. We don't know that because this single assertion fails, this one test fails. Okay, so test cases and methods are obviously assertions, and we have asynchronous tests and expectations, which are things that run and we're expecting, but they run asynchronously, and we're expecting something to happen after a certain amount of time. And then we have user interface tests um, and performance tests. So we won't be doing any performance tests. We'll be doing UI tests and with assertions and unit tests of logical components, obviously with assertions as well. So the resources available to us, obviously, there's the official book of Swift. So Swift is now independent of Apple, but obviously they're the drivers behind it and the main users. Swift UI itself and XeTest has its own page. Okay, but let's actually go and actually dive in now and actually have a look at the development environment, look at its similarities and differences between Android Studio. So, um, although we're using Android Studio to do Android development, if you don't like Android Studio, you don't have to use it. You can actually do Android development in any um, IDE. You can use Xcode, Visual Studio, whatever you want to use. It's not necessarily as straightforward as using Android Studio, but you can do it because at the end of the day, everything is just a text file. So it's either XML or KT file, and we can edit them in our favorite editor. It's not a problem. You cannot do that when you want to develop an iOS application. You could write the code in some other IDE, but if you actually want to build the application, you have to use Xcode. Now, a long time ago, a long time ago, I'm trying to picture it back. This is going to be 20 years or so. Um, there was an Apple development environment for Windows, but in actual fact, there was one for Windows, and there wasn't one for OS 10. That very quickly changed. Policy changed inside Apple. They dropped that and they introduced Xcode purely for Mac. You have to use it. Now, it's big, it's complicated. Um, the the an upside is that it's sophisticated. And one of the things that is good about it is the code coverage analysis that's built in. So you notice in assignment 2 and 3, we didn't do code coverage analysis. You can add that in to Android Studio. It's tricky and a little bit flaky, um, which is one of the reasons why they don't provide it themselves. It's a third-party library that will actually do that. But Xcode actually has this built in. It's now switched on by default. It used to be the case that in Xcode applications you had to remember to actually switch code coverage analysis is on. It's now the default, which, as it always should have been, and it's really easy to navigate. We'll have a look at that when we have a look at a couple of examples. Okay, so if you all want to fire up your Xcode, I'll put into Google Drive. Just give me a moment. Um, um, Example which we can open just to have a quick look around. Let me just find the right place. Alrighty. So I'm just putting into the Google Drive 07.helloworld.zip. So someone want to give me the thumbs up in Zoom when you can see that. Oops, I lost my thing. We can see it. Okay, so download that and unzip it into somewhere new. It's worth pointing out whilst you're actually doing that, the folder that you unzip it into can actually be named anything. The name of the project is defined by the project file that's within it. So once, let me just leave that. Where are we? No. So you can either do file open. I'll bring this over here. So you can either do file open, or you can just double click on the hello world project file, and either way that will actually open this up. So let's give you a couple of minutes. People, just give me a hands up in the participants when you've got that open, and we'll have a bit of a walk around it. With you coming in. Give it a couple of seconds to get that open. Having a problem open it, just stick something in chat so we know what's happening. Well, I'm going to assume that we've only had a couple of hands, but I'm assuming that everybody's actually got that open. If you're zooming in, if you've borrowed a Mac and you're zooming in on your Windows machine, obviously you've got mice and keyboards flying all over the place. But okay, so this Hello World example has had its tests removed. If you were to create a brand new project, it would generate some default tests for you. We'll come on to that into the next example we'll look at in a moment. So Hello World obviously expands so that so Hello World is the project. We can see some properties of it. We're not particularly interested in those at the moment. But at this level, this is the actual app in the Hello World folder underneath the Hello World project. In the example we'll look at in a few minutes' time, there's another component at this level, which are the tests for Hello World. This little one, or tests for whichever project we're working on. This one doesn't have any. So beneath that, we have two things. We have some assets, which we don't really need to worry about, but these are the things like icons, images, text, and so on. A bit like the values XML in Android Studio, but not exactly the same. You're more than welcome to look at that, but we don't actually have anything for instance in here. We could give it a specific application icon if we wanted to, but we haven't. We don't need to. But then, in all cases, even in this very simple app, it's split into two. So we have the view, which is the visual part, and we have the app, which is the entry point. So remember in Android we had the main activity, give or take. The app is the equivalent of that. It's the entry point into our app. So if we have a look at that, it's very, very simple. So we have a number of things going here. Obviously, we need Swift UI. We'll be looking at that in a little bit more detail after the break, and in a lot more detail on Tuesday. We have an annotation here at main, which tells the Swift runtime, the Objective-C runtime, that this is the entry point into the program. It's like the main function in a C program. And notice it's a struct. It's not a class. It doesn't need to be. It's just a struct. It's called Hello World app, and it extends the app structure, which is built into Swift UI. So notice that we don't need to do implicit imports of individual classes or structures from this package. Just by importing Swift UI, we get the definition of app. We don't need to import it individually. Excuse me. And then we have the body. And this sort of has a little bit of sort of almost a web sort of flavor to it. This is the body of the application. And in any application, we need at least one scene. We'll come on later on more detail on what scenes are. And then a scene is typically, as it is here, made up of a window group, which is basically a number of views, a number of screens, that depending on our program logic, we could move between to something like navigation. There are actually navigation components, but we need we need at least one scene. We need something that's an app. It has to have at least one scene, and typically that scene will have a window group in it, and that window group needs to have at least one view. So all the apps that we're doing are going to be like this because they're simple. Even when we get into assignment 6, so this is just getting things going. There's no visual componentry here. This is just getting us up and running. So the main event is the Hello World view. And notice we don't need to import it because it's just part of the app. And this is the bit that we'll actually see. So a number of things to notice about the Hello World view. Again, we're importing Swift UI. Yeah. Again, we have struct. Hello World view extends the view struct. So we're getting that from Hello World. And then we'll look at what's actually happening here. But down at the bottom, we have this thing called a preview provider. So we could actually name that anything we like. Content, we could actually name that Hello World. Oops. Hello World previews. It can be named anything you like. Yeah. This is the new AI-driven code completion, which I really don't like. But so the bit down at the bottom here, again, it's a structure. It extends a preview provider, and we can actually call it anything we like. But what this is doing is it allows us to have this thing on the right, which allows us to view it inside the IDE without starting up a full-blown simulator, which is, we can zoom in a little bit. Which is quite handy, especially when because this is the entire application. But if we're writing a little UI component that isn't the entire application, it's just one component, and we actually want to see what it looks like, we have this preview that we can see inside the IDE, which is kind of nice. Top tip, when we get into assignment 1, and sorry, assignment 4, 5, and 6, when you're actually looking at code coverage, in order to get perfect code coverage, you would need to actually comment out the preview. There's been a change in Xcode 16, which makes it difficult for us to have a preprocessor directive to exclude the previews from code coverage. So basically, just before you submit, write this down, comment out your previews, otherwise you'll get less than perfect code coverage. It's not an ideal solution, it's a bit of a hack, but don't forget to do that, otherwise you'll get dinged for not having perfect code coverage. Okay, so over here, I'm not, no, the review panel, it's been there for a long time. I think they introduced it at iOS 10 or something, it's a long one, yeah. Excuse me. And remember, this is all running locally. There's no simulator going on here. But if we actually want to run it in a simulator, we can choose which one we want. I'd recommend a 16 Pro. It's pretty new, or a 16. Either way. But choose something fairly new, so that when we actually run it, and it will actually change the preview as well. When we actually run it, just by clicking the run button, So in the same way as we did in Android, we get a simulator, and our emulator pops up, and then we get the running application. Now notice that when we ran the application, the preview was paused. So you cannot have the live running application and the preview simultaneously. I'm not entirely sure the technical reasons for that, but you certainly can't. But when you're actually laying out a component on the screen, having the preview there's kind of handy, rather having them to continually compile and redeploy the application to the phone. So we can actually close the simulator. Oops, didn't mean to do that. No, I didn't want to do that. I wanted to run it in the preview. Now, this is a very common thing in Xcode. It has a habit of crashing out on you, which is unfortunate. But let's just do this in the preview. Right. So whether we run it in the simulator in the preview, what does this very, very simple app do? So what it does is if we type in, so you can try that. As we type, it echoes into the field underneath. Oops. Okay. And it has a little logo and some text at the top. So let's actually walk through on the left where that comes from. So we have our body again, yeah, which is some view this time. So some view is basically saying it's a view, but I don't quite know what it's going to be yet. And so we start off, so at the outer edge, we have something called a vertical stack, which means the components we're about to put in will appear one above the other. Excuse me. And at the top, we have an image. Yeah. So basically, this is a little globe that appears here. Yeah, if we take that out, yeah. Notice that the preview refreshes as we change the code. Yeah, which it obviously doesn't do when we're actually in the simulator. So we can put that back in. Comes back. Yeah. And we could change what the thing was. There's lots and lots of different built-in images you can use. And then underneath we have a little piece of text. Again, if we take that out, we can see it disappear. Put it back. And they're vertical because they're inside a vertical stack. And underneath we have a very simple form down here. So again, if we take that out, we can see where that is. Feel free to run along. Back. And there's our little form. So the form is actually this entire gray thing. Now inside the form, we have a text field, which we can type into, which is this guy here. Yeah. And then we have a text, which is just a label underneath, which is obviously this guy here. So that's pretty straightforward. But the magic happens to do with this guy here, line 5. So this has a decoration on it, ampersand state, which marks this private variable. So it's mutable. So private, only it's not visible outside this struct. It's a variable, so it's a mutable piece of data. It's called name, and its initial value is an empty string. And it's state. So what we're actually doing here on this text field, what we've said is that whatever the user types into here will change the value of this state variable. So remember state when we get to doing cross-platform. So whenever we type something in, so just type in a single letter, the state variable name will change. And as a consequence, the value that appears in this label will change. So as your name is space and then the value of name. So the backslash and the parenthesis is inserting the value of name, the current value, into the string that appears. So if we type another character, so now I've got 2, and that doesn't matter what we do. We can select, we can cut that out. and we can paste it in again. Yep. So it doesn't matter how the value changed, it just changed, and as a consequence, this element will respond to that change in state. So although this is a very, very simple example, there's a lot going on here. And the most important bit is the state. Excuse me. So if you think about the login dialog that you've done in assignment 3 in Android, at some point, it should come as no surprise, is that you're going to be writing a login dialog in Swift and Swift UI. So responding to what the users type in, you're going to be holding the name, email, and the password as state variables. Okay, and as we've seen, we can actually run it in the simulator, and it will pause the preview. This is just a last check once you've got things working in the preview, just to make sure it will successfully deploy to the phone, and then you can just make sure it still works there. She does. Okay, so that's our sort of first little Hello World application. It's actually a stripped down version if you were to just do a file new project yourself, because the thing that we're missing are the tests. Oops. That's the thing, it's the usual crashy thing. Okay, so let's actually going to have a look at a slightly more advanced version, which is advanced project, which is the infix calculator. So we on Monday last week we looked at this for it was our very first sort of Kotlin little exercise, and let's just find the right project for that. Okay, now let me pop this into Google Drive for you as well. Just give me a moment. So this is going to come in as 07 infix calculator.zip. Again, just give me the thumbs up when you can see that. Well, there's a question there about the Mac Mini and signing into Xcode. If you've got a problem doing that, you can you got a choice. If you already have an Apple ID, you can actually use that, or you can create one. But if you've got a problem actually getting Xcode installed, as soon as this morning's sessions is over, go along to Ishmael's office hours and he'll be able to get you sorted out. But follow along with what we're doing now if you haven't been able to get Xcode installed, so that you can repeat this once you have got it in place. Okay, all right, so again, do the same thing, just unzip it into a folder. The folder can be called anything you like. Tradition says it has the same name as the project, so you would create a folder called infix calculator and expand it into there, but you don't have to, you can call it anything you like. Probably the only wrong place to store it is on your desktop. I know your generation love the desktop, but it's not a good place to store anything. Yeah, there we go. So there's some help there from your classmate from Zion. Perfect. Thank you. Alrighty. Okay. So let's go and have a poke around inside in this one. So again, we start at the top with the infix calculator, but at the top level, we've now got a couple of new things. This thing here is the test plan, which we'll come back into a minute. But we still have our the actual app in the infix calculator folder, which we'll expand in a minute. And then we have non-UI tests and UI tests. So let's just gonna have a look at the infix calculator. So again, we've got some assets which we're not actually using. And then now we have three things that we actually care about. So again, actually maybe just run up the in the preview. Should I come into a minute? Oh, actually, no, let me not do that. Let me actually just run it in the app before we look at code. Excuse me. So this is our infix calculator. It's the classic, 1 + 1 = 2, as opposed to your postfix calculator, which you'll be doing. Okay, so what we're going to be able to want to do is 1 plus 1, oops, and evaluate that. So, yeah. But if we get a problem, yeah, so just pause. We need to be able to handle the error, which is why we've got this additional class in here. So we have our mfix calculator, which is just straightforward Swift. There's no UI in here at all. So notice we're importing Foundation, not Swift UI. So if we import Swift UI, we get Foundation as well. But here we don't need the user interface, so we just want Foundation. This basically means import Swift. And so we have a class. So it's not a struct, it's a class this time. It doesn't extend anything. It's a standalone class that we've invented for ourselves. It has a function called pause, as we had in the last week's example. It takes an expression. It returns a double, as we can see here, but it also is telling us that it might throw an exception. Yeah, an error. So there's a lot going on here on line 5. Obviously, it's a function, it's full parse, takes a string as its one and only argument, returns a double, and it might throw an error if something goes wrong. Yeah, which is why we actually have infix calculator error as a class. I beg your pardon, as an enum. An enum is an even simpler version of a struct. So here we've actually got two different possibilities for an error that the infix calculator could throw. One is that it's an invalid expression, completely invalid, or it would otherwise be a valid expression, but the operator supplied is invalid. It's an operator we don't support. So our infix calculator, ignore this commented out bit for a minute, it's basically going to say if we don't have at least, we don't have three, but this is not fully functioning, by the way, it's just a very simple one. If we don't have at least three separate operands, we don't have enough, so we're going to go about invalid expression. Excuse me. And then we actually we have a look at the first three, and if it's not plus or minus, we're going to throw an invalid operator. So if we do 1 plus 1, that's going to work. If we do 1 minus 1, oops, it's going to work too. If we do 1 divided by 1, that's not going to work because over here we don't support it. So it's throwing an invalid operator, and we're actually saying what the invalid operator was. Although in the UI we're not responding to that, we're not displaying that. We just said there's an error. So that's the infix calculator, which is standalone Swift. It doesn't need a UI. So importantly, we can test it without a UI. So if we actually have a look at our infix calculator tests, these are the tests for that class, and these are non-UI. So they're just very simple, the same as the ones we saw when we're doing this in Kotlin. So we have again, a final means it can't be extended. It's a class as opposed to a struct or an enum. It's called infix calculator tests, and it extends xc test case, which we've imported from here. And notice here at line 3, we've imported the thing that we want to test, because infix calculator is not in the same scope as the test, so we have to actually get hold of it, and that's what the line 3 is actually doing. It's saying what is the thing that we're actually going to test. Excuse me. And then we have some simple addition, simple subtraction, unknown operators, and invalid expressions, and so on. Right. So if we actually run these tests, if we actually go to our little testing tab here, collapse that for a minute. So here are our, we can run an individual test, or we can run the test case, so the suite of tests. So we'll run the test suite. I'll do a little bit of a build. And it actually created, even though these are non-UI tests, it creates an instance of the simulator in which to run them. Yeah, which you did. I noticed it says that this is a clone of something that we already had. Yeah. And it fired up the application, but never actually used it. And we passed all the tests in the case, and we passed each individual test. If we want to run an individual test again, we can. We can just click on it and run it. No, we'll just run that one test. So that's handy if you failed, if you passed most of your tests but failed one of them. It's handy to, and you change your implementation, it's handy to run that one test again. So here's the example that we had when we were looking at some secret source from assignment 1. We can the rounding is actually happening here in the evaluate function. Yeah, so you can try it without it and demonstrate that that actually fails. So those are non-UI tests, but notice it does actually fire up a version of the app in the simulator because it has to. It has to actually fire something up. It can't run these on your Mac because they're not Mac tests. They're iOS tests. Your Mac is not running iOS. It has to fire it up into an iOS device to be able to actually do that. Okay, so we'll come back to tests in a minute. So that's the non-UI tests, the unit tests, and we also have UI tests. But let's actually look what the UI is doing. So again, we have our app identical to the one we saw previously in the Hello World, except that it's creating an infix calculator view rather than a Hello World view. So we've already seen the calculator error. The infix calculator view, again, we can fire at the preview. So same kind of thing. So basically, we're importing Swift UI. It's a struct called infix calculator view, extends the built-in view. We have two pieces of state, the expression that gets typed in and the result. Same kind of thing. If we look down here at these, the text field here, this is the bottom one, which has where it says result, that is the hint for typing in. Its value is whatever the result is, and it's disabled. So it's not a text field. It's not a label. It's a text field that's been disabled. So we can't actually type into it, whereas we can type into the expression. Excuse me. So some of the things to notice about this layout, it is a nested vertical stacks. So on the outside, we have a vertical stack saying everything inside me is going to be one above the other. And the reason we do that is because we want this spacer in here to take that spacer out. Oops. You're doing some weird stuff again. It will just put whatever we want actually in the middle. So a spacer expands to fit the space available. If we don't put it in, our calculator appears in the middle of the screen. If we do put it in, it appears at the top, but only because it's inside a vertical stack. Yeah, and then we have another vertical stack, which contains the label in there. Yeah, infix calculator with no system image. And then we have another vertical stack, which contains the two text fields. It's not a form this time, it's two text fields. And the button. But the button is in a horizontal stack so that it appears in the middle of the screen. Yeah, so if we took the horizontal stack out, maybe I didn't need that. Maybe you needed that in previous versions. But anyway, so we've got the evaluate button in the middle, and importantly, we have an action. So when we click the evaluate button, what's going to happen? It's going to run this function here. So this could potentially throw an error, so we're actually going to catch it. We create a new instance of the infix calculator, which is the one obviously we tested, which is this guy here. So we create a new instance of it. We call We can tell it's a new instance because it's got the parenthesis on it. And we're going to call parse, passing in the expression, which is this piece of state, which comes from whatever we typed in here. That is the expression. We're going to give it to the infix calculator, and the string that comes back, we have to get hold of its description. So a string in Swift is a complex object. It's not a simple thing. So we get hold of this description, which is as we would regard it as the string that we'll see, and we put that into the result piece of state. And as a consequence, this text field's value will change. So make it 3. Oops. Another 3. Evaluate. It comes in as 5. And then if we get it wrong, so if we say we have, try to divide 1 by 4, evaluate on that. This calculator parse throws an error, which we catch, and we actually ignore the text on it and just say error. Okay, and then down at the bottom, we have our infix calculator previews. These preprocessor directives don't work in Xcode 16 because the test suites are generated automatically, and for some reason they took out the ability to add a preprocessor directive into them. So again, top tip, write this one down. When you come to submit your solutions, comment out your preview providers. Okay, so if we go back to our testing tab, which is this guy here, and we can run our UI tests. So if you have a look at them here, again, it's an XC test, it has 2 tests, very simple. And importantly, really importantly, at this point, we are just testing the user interface. Don't retest your functional components in your user interface test. So we're not going to put in lots of crazy expressions and do lots of different complicated things because we've already tested that in here. So we don't rerun these tests. All we're testing is new functionality for the UI. So there's only 2 things we need to test. One is that if we give it a valid expression, we get the right result, or we get a result. And one is that if we give it an invalid expression, it says error. And that's all we need to do, because everything else to do with testing the infix calculator is done in the non-UI tests. Yeah. So this is something you have to keep an eye on yourself. Don't repeat. All we're doing here is testing the user interface. We've already tested the calculator. All right, so we got a easy tab. We can actually run those. So that'll actually run the UI tests. Obviously, that very definitely needs a simulator to be able to do it. And the same as we had in Android, it manipulates the running app as we're running the test. So that actually ran by its own choice. It ran them out of sequence, and they both passed. Okay, so if we actually, and then we can actually run them all just by running this one here at the top, and this will run the non-UI and the UI tests, and it will run them simultaneously. So if you look sort of behind the scenes, Xcode is creating simulators all over the place because it needs one for the non-UI tests and one for the UI tests. If you have more than one test case, so say instead of having one test case, we had 2 or 3 test cases. If you let it, it will bring up a phone simulator for each test case. So you can end up with 4 or 5 or 10 or 100 simulators running simultaneously, which is fine if you've got a powerful machine, but if you haven't, you'd want to figure out how to get it to run them sequentially. But in our little apps, it should be fine as it comes out of the box. Okay, so that's actually running the tests. Now, the last thing that we care about is our code coverage. So if you go to this tab, which is called the Reports tab, the last one, and beneath it, it shows you the runs that we've done. Obviously, this is the latest one. We did the one a little bit earlier on, and so on. One is the one at 10:11, the first one we did. But what we care about is the coverage report. So if we select that and expand it, see it's 97%, and we expand it, and we can see that the Infix calculator app is 100% covered. As we would expect, there's nothing really there. The Infix calculator itself is 100% covered, whereas the view is not. So we expand that, and we see that the Infix calculator view previews has not been covered by the tests, which is correct, it hasn't. So if we wanted to get perfect code coverage, we go back into here, get rid of the preview. Obviously, the preview isn't there, so it disappears. And then if we should rerun our tests, and we'll actually rerun them all. Oh, actually, no, let me just stop that. I'm going to make one other change as well. I'm going to, in the Infix calculator, I'm going to add in a piece of code that is not, we're going to get a missing branch because we're never going to have more than a 1K of operands put in. So we go back our tests, we're going to rerun all our tests. We'll get better code coverage on the UI, but worse code coverage on the non-UI because we've added in a deliberate piece of code to get bad code coverage. And we can see here the UI tests are running. Can actually watch them. Oh, that worked. Go back to the report. Got a new run, 99%. So if you have a look at the view, we're now at 100% on the view, but the calculator itself has got some missing lines, and it will actually show you inside the IDE which lines are not covered. So basically, it never goes into line 12 because we never give it more than 1K operands. So obviously, we decide we don't actually need that code, take it out, run our tests again, and this time we should get perfect code coverage. The non-UI ones run quickly, and the UI ones run a little bit slower, especially any test that is waiting for something to appear that never actually appears. So now we're 100% on our code coverage, that little app. Okay, all right, so that's a quick run around Xcode and simulators and so on. Okay, kill all these guys. Okay. So what we'll actually do, we'll take a break now because we're almost 10:30. And after the break, we'll look at some more Swift features and some more Swift UI. And then importantly, we'll actually have a look at an introduction to assignment 4, the first iOS assignment. All right, so let's 10:30. Let's aim to be back here at 10:45. Get a good start so we can take our time through this important stuff. Okay, so back here at 10:45, and we'll carry on.